Is the world we see nothing but an illusion? Physicists have proven that the universe does not exist, and it's really true what we think is real doesn't actually exist from a scientific point of view. Everything is a perfect illusion, as if created. For us, we live within this illusion and explore it. Now we are on the verge of a breakthrough to uncover the biggest lie of all time. Is matter really real? It seems so. When you put your plate on the table, it stops, and you can take the food into your body. You will notice that this act has an effect. You hear your digestion and gain strength through the food. There is no question that the world of matter exists. Somehow, we can kill ourselves with weapons, or rather destroy our bodies in the material world, but recent studies show that the world of matter is nothing more than a hollow projection created for us to experience as protagonists. In this world, we may be far more than we appear to be. We may in fact be something quite different from mortal bodies with a brain and a heart. So far, scientists say that when the body is destroyed, the human being dies, and quite a few scientists claim that this must definitely be the end of life in existence, but there is evidence that our bodies are just condensations within three-dimensional space, possibly controlled by what religious people might call a soul. Similarly to Avatar, we could simultaneously exist in another world, sleep there and dream, our lives as avatars on Earth. Then this world here would be nothing more than a puppet show. In a way, we ourselves are players and protagonists, but most of us are not aware of this. The theory of relativity is not the measure of all things. Was Einstein wrong when he proposed the theory of relativity? Some modern theories, such as quantum gravity and strength theory, call his assumptions into question. The theory of relativity does not work on a microscopic scale. Quantum physics and relativity often contradict each other. There must be one or more levels that unite the two. There is no other way, because quantum theory is the theory of the world of the smallest particles, the quanta of light. And these are the building blocks of all large phenomena. Einstein's the theory of relativity refers to the universe as space to stars, planets, and the effects in the world of visible objects. But these objects are all made up of light, quant, and they do not behave as if matter is real. Einstein's theories remain fundamental, but science is evolving at the moment. We're at a point where this type of physics is no longer getting anywhere. The latest discoveries of the James Webb Space Telescope can no longer be described with the old physical, the per Einstein's concept of space and time must have been incomplete. Quantum mechanics reveals phenomena that his theory does not explain. Black holes and singularities contradict the general theory of relativity. In some important points, the existence of dark matter and dark energy remains a mystery. Space and time might not be fundamental quantities, but much more flexible than previously assumed. The connection between gravity and quantum mechanics is also still unclear. The latest findings show that gravity may not actually be a force, but rather a curvature of spacetime caused by masses and energy. Some scientists suspect that space and time itself could consist of tiny, quantum-like structures. These structures could behave in ways that we do not yet fully understand. They may possess some kind of intelligence or represent some form of force or life that we could not yet imagine. There is evidence that the physical forces in the universe have changed over time, which would suggest that the universe is undergoing some kind of evolution that resembles life. Einstein's work is a milestone, but the search for a unified theory continues. However, if it turns out that the universe is just as changeable, a hollow projection as we are, we have a poor chance of approaching the truth with the old methods of physics. Then we will need superperception or completely new branches of science to unravel the mystery of the cosmos. How does hollow projection work, and who creates it? So if everything is just a hollow projection, where does it come from and how is it structured? The idea is essentially based on the concept that all the information that creates our three-dimensional universe could be stored on a two-dimensional surface. This theory has its origins in quantum mechanics, and the general theory of relativity. Quantum mechanics discovered that quanta are nothing more than information carriers that are incredibly changeable. They can become a table and thus convert the information of a table to planet Earth, or they can become any other matter. But even if they form themselves, they have the fascinating property of immediately dissolving their form again. If they are not measured or observed in quantum physics terms, this means that your table disappears when you or nobody else is looking. Hollow projection theory assumes that our three-dimensional universe is just a fairly loose projection of information stored on a two-dimensional surface. The idea originates from physicists such as Gerard HFF and Leonard Susskind, and was first introduced in the late 1970s. The decisive factor was the observations made in the vicinity of a black hole, which showed that the amount of information contained in a certain volume of space is limited by the surface of this volume, and not by its volume itself. This contradicts the classical understanding of information and space, and could mean that the spatial dimension themselves could be wandering phenomena controlled by deeper physical levels in practical terms. This would mean for our known universe that every piece of information required to construct and maintain this projection is theoretically stored on a two-dimensional surface at the edge of the universe. This information is then projected in such a way that a three-dimensional space with material objects and physical phenomena appears optically a universe of pure conscious. Our brain plays another key role in this scenario. We can only perceive the world and the universe through our brain and our senses. We basically do not see what is really out there. We only see what the brain lets us see in the holographic universe. Gravity is a result of the projection of information from the two-dimensional surface. This means that gravity is not really a force in the traditional sense, but a dynamic property of the holographic projection. In a holographic universe, we play an essential role as conscious observers. We could be experiencers and creators in equal measure. Now, it has not been scientifically proven that a table really disappears when nobody is looking. Nor can we monitor this in an experiment, because the camera with which we observe would be equivalent to a measurement that maintains the shape of the table. Another exciting idea in this context could be the role of consciousness. Scientists don't really know what consciousness is yet, but it's certainly instrumental in shaping quant from the wave to the particle state. Now, it could be that the whole universe is infused with a kind of consciousness that shapes and sustains it. Our consciousness is only a part of the greater whole of consciousness, and we are co-creators, but we don't have to worry about the table remaining a table. For example, is the speed of light. The problem, do you remember from your school lessons, that the speed of light is the measure of all things in space? Einstein spent his life researching the forces and phenomena in the universe, and came to the conclusion that all phenomena and forces are dependent or relative to each other. Time is dependent on the location of the observer. Acceleration influences time, and the speed of light supposedly sets absolute limits. But this could be a mistake in our physics. If the nature of light is possibly completely different from what we have imagined so far, this could mean that all our observations and conclusions of the last 100 years are wrong. The light we see is quanta, and we now know that they behave very capriciously. So how can the speed of light be a stable measure? It's possible that we have created limits for ourselves through this view, and constructed a false image that we now need to revise in reality. Light could be much more dynamic and changeable. But what would that mean in relation to our observations of the early universe? If the speed of light were indeed variable, we would have to completely rethink our models of cosmic evolution. The observations of the cosmic background radiation that have so far provided us with information about the early universe are based on the assumption of a constant speed of light. Variations could mean that all our calculations of distances and times are wrong. Then our estimates of the age of the universe and the speed of its expansion would also be wrong. This could explain why the Webb telescope shows us galaxies that are so old that they shouldn't even exist. We normally measure the age of galaxies using the redshift of light. When the universe expands, the light is stretched and changes to a reddish color. However, if the speed of light is not constant, our measurements of the redshift are also incorrect ultimately. However, this does not mean that Einstein, Hubble, and all the others who built up our cosmology were frauds. They just delivered the best possible work and explanations. For their time and era, they seemed to work very well for almost 100 years. But now it turns out that these theories are incomplete, and we need to open up our science to new dimensions of truth. We could possibly explore a holographic universe only through our minds, but we still have to learn the techniques to do. So think about it. In the 1970s, there was a man with supernatural sensory perception who could only examine Jupiter through his inner spiritual vision. Ingo Swan's work is often hushed up today, but Swan described the planet's atmosphere almost perfectly and even saw its fine rings, which were only discovered by the Voyager 1 probe in 1979. Before we become such superbrains, the age of quantum computers will probably dawn. These extremely powerful computing machines should, among other things, help us to better understand the true nature of the universe and show us where our previous mistakes lay. Click on the subscribe button now and be part of every new video.